Hello, my name is Ethan Farber. I'm a graduate student at Boston College. I'd like to thank the organizers of the Tech Topology Conference for giving me this opportunity to speak about a family of pseudo-Anosov braids that I've been thinking a lot about recently. I'll start this talk off by mentioning the main results, which is that for each integer m, at least 2, there's a family of pseudo-Anosov braids P of m, indexed by the rational numbers in the open unit interval. And these braids have 3 very nice properties. The first is that this fractional number, a over b, is the fractional part of the fractional Dane twist coefficient of beta sub a over b. And that is a geometric invariant of these braids. Each of these braids is also pseudo-Anosov, a dynamical characteristic. And each of these braids is moreover positive, which is an algebraic characteristic. One thing this is saying is that through these families P of m, I can produce infinitely many braids which are positive and pseudo-Anosov and have whatever fractional Dane twist coefficient one would like. And what I'd really like for all of us to come away from this talk with is the following image. So here on the left is a picture of the fairy tree. It's a tree whose vertices are the rational numbers in the open unit interval, and they are connected to each other by edges in some combinatorial way. And on the right, I've drawn P of m in a very suggestive way. P of m, in fact, carries this same structure. And I'll say a few more words about that in a second. But first, I really want to emphasize that this family P of m isn't just magicked up out of nowhere. It's really coming from a very particular construction. And that construction takes as input interval maps with very special combinatorics. The point of these special combinatorics is that we can thicken the interval into a disk, and special points on the interval will become the punctures of the disk. And the special combinatorics ensure that when doing this procedure, the induced map on the disk is a positive and pseudo-Anosov braid. Okay. So in short, we have a process for taking in a special interval map and outputting a braid beta of f that is positive and pseudo-Anosov. On the other hand, from the dynamics of f, we can code some particular orbit of it and produce a rational number a over b. Okay. And for this reason, we call the thickened braid beta of f beta sub a over b. Okay. This coding has a really nice property, which is that if a, b, c, and d satisfy a very simple relation, then we can take the interval map whose coding is a over b and the interval map whose coding is c over d. We can concatenate those codings and they will produce a third interval map, which is also in the family. So it can also be thickened to a positive pseudo-Anosov braid. And its coding produces for us the rational number a plus c over b plus d. So that is called the mediant of the fractions a over b and c over d. And this is really fantastic because that relationship, that taking medians, is exactly what's being encoded by the fairy tree. It is telling us when one rational can be made as the mediant of 2 other rational numbers. And this structure on the family of interval maps has very strong implications for the dynamics of the braids made from them. And we can use this structure to study these braids very in depth. Okay. And I'll finish off by just restating this theorem. For each m that you give me, I can make a family of braids, P of m, where m is really telling us the number of critical points of the underlying interval maps. And these braids are indexed by their fractional Dane twist coefficient. They're all pseudo-Anosov and they're all positive. And taken as a collection, their family carries the structure of this fairy tree. So thank you for giving me this opportunity to speak. I look forward to the Tech Topology Conference, and I look forward to talking to you more there. Thanks. Bye.